Our goal in this set of slides is to characterize the different kinds of behaviors that we can see out of 2 by 2 linear systems. And so also to build a little bit better understanding of what it means for a system to be stable and make the idea of modes a bit more intuitive. So when we started off with a second order differential equation and then wrote the state space form, we had a particular structure to that A matrix, one that looked like 0, 1, minus A0 minus A1. So when we look at a generic second, not a second order system, but in this case a 2 by 2 linear system, now we can put kind of arbitrary elements on all of these entries, and so now we have an A matrix that's very general and looks like this. So you can imagine that this would be something that maybe would need to be written by 2 coupled single order differential equations, not a single second order differential equation. So, but this case of second order differential equation that fits within this context, here we just make this a 1 and we'd make this a 0, and then that would fall in line with what we looked at before. So in this, but this higher kind of more general linear system, we can compute the eigenvalues, because again, that's what's going to dictate the stability and the overall trajectories of the system. We can calculate those, and these are still going to be all symbolic. So when we calculate the determinant of A minus lambda I, we just take this determinant and we get this expression, and by grouping terms, we have a linear coefficient and the constant coefficient. So when we look and solve that characteristic equation using the binomial formula, just like what we did before, we get something that looks like this, where again, this is Q is the constant coefficient and P is the linear coefficient. And one of the things you'll notice here is that P is the sum of A11 and A22, which happens to be the trace of A, so it's the sum of the diagonals. Q, which is the constant term, ends up being this product minus this product, and that's the determinant of A. And so those also have some kind of intuitive meaning. So what ends up happening is we use the binomial formula to get the different eigenvalues that characterize the solutions, because remember, the two solutions are going to be characterized by e to the lambda 1t and e to the lambda 2t. And so these are kind of what characterize the two different modes of the system. And so when we talk about modes, one of the ways you can kind of think about another area where this arises is, say, in like a guitar string. So we know that if you were to pluck the guitar string, it can vibrate in kind of mode 0, which is the whole thing bending up and down, or it can make more essentially more ups and downs along the way. And so you can imagine the first harmonic, the second harmonic, the third harmonic as being adding essentially one more sinusoid in the between the endpoints of the guitar string. And so the overall vibration of that string is going to be a combination of all these different modes. So modes is really just a way of us breaking down a complex behavior into more modular pieces that can be described in a single term. And so that's really what we're going to be looking at, these different modes. And again, in the context of state space systems, the eigenvalues really characterize essentially the stability and the behavior of those different modes. And since lambda comes from a binomial theorem or binomial formula, we get essentially, in general, you get complex valued eigenvalues. So you can get complex values, and so when they are complex, they come as complex conjugates. So you get something alpha plus or minus I beta, where alpha is the real part and beta is the imaginary part. You can get specific cases, so where, for example, these terms here end up being 0, so p squared minus 4q, remember that's called the discriminant. When the discriminant is 0, then you can have a variety of different options. So in that case, you can also get cases where the discriminant is 0, or you can get a case where the discriminant is positive. And so in both of those cases, you get real valued. And so you can either get both of your eigenvalues being positive, you can get them both being negative, or you can get them being opposite signs. And so what we're going to do in the next couple slides is we're essentially going to look at all the different possibilities that you get and the types of trajectories that you would see depending on these different types of eigenvalue pairs. So if you remember going through lab 1, you watched a video about phase plane portraits, and so we're going to use phase plane portraits as a way of understanding the trajectories of these systems and characterizing the entire solution of the state space system, both x1 and x2. So in the case where we have essentially opposite signs, but they're both real, so both real valued eigenvalues, but one is positive and one is negative, the overall solution we know will look like this. And so this is going to be the first mode, and this is going to be the second mode. And so again, those eigenvalues characterize whether those are going to be stable or not. And so we already know that the real value of the real part of these eigenvalues need to be negative for this solution, the overall solution, to be stable. And in this case, they're both real, so that means they both have to be negative. In this case, they're not both negative, so one of them is positive, so that means that this is not a stable solution. So when we look at the phase plane portrait of this, we look at the way that x changes over time. And so remember, essentially you think about picking a point and starting there, and then you follow these vector fields through, and that ends up being the solution. And in this particular figure, I'm borrowing it from a really nice website, and I would recommend going there if you want to dig into this a little bit more or see it from a different perspective. The only tricky thing about this is that in their figures, their vector x, which we call usually x1 and x2, they call x and y. So that's why you can really think of this as being x1 and think of this as being x2 instead of x and y, if that helps. So the way that this vector field works is the fact that we plot the eigenvector directions. So this is a vector and this is a vector. And when we plot those vector directions, that tells us essentially some of the orientation about this, this particular phase portrait. So one of the things we know is, in this case, we're going to assume that the first one is the negative one. So that means that the mode corresponding to lambda 1 is going to be stable because it has a negative real part. And so in the direction of V1, if you look at the part of this that is in V1, right now it's at some kind of rather large value. Then it becomes smaller. Then it becomes smaller. And it continues to become smaller. So the portion of this overall solution that's part of mode 1 gets smaller and smaller. And so that's what it means for that mode to be stable. In contrast, if you look at the part of this that is in the V2 direction, so in the second mode direction, it's small, it's getting bigger, it's getting bigger, and it's getting bigger. So it's going further and further along this direction of this mode. Whereas here, this is getting smaller and smaller. And so this is one way of understanding the overall trajectories of the system in terms of the stability of the two different modes. And so when we talk about a second order system that we convert to state space, one of the states is the output y, and one is the derivative of the output. But in a more general case, we can think about this as just being x1 and x2, two different quantities that represent the state. And so these curves demonstrate the different types of solutions that you get for different initial conditions. So if you were to start here, you would trend in this direction. But the stability, which is characterized by these lambda 1 and lambda 2, once you drop these v1 and v2 down, which are the eigenvectors, it's the stability of these lambda 1 and lambda 2 that generate the overall picture. And so in this case, we know that all of these are leaving. going along the V2 direction, but all of these are going in along the V1 direction. And so that's a characteristic behavior of a saddle. When both eigenvectors are real and they're not equal to each other, so that means that either they're both positive or both negative, then you can either get a stable node or an unstable node. So if they're both stable, so if lambda1 and lambda2, we know that they're both real. So if they're both negative, then that means that both solutions trend to 0. And so that means, again, if you start here, the contribution in mode 1 is large, and then it gets smaller, and it gets smaller. The same thing is true for V2. It's large, it gets smaller, and it gets smaller because the amount in V2 is decreasing. So both of them are trending towards 0, so all these solutions will go to the origin. In this particular case, you can see that that V2 is going a little bit faster than V1. The mode of V2 is going a little bit faster than the mode 1, and that's because this slope, you can see that between these 2 points, the mode 1 amount changed this much, and the mode 2 changed this much. So mode 2 is changing faster than mode 1, and for that reason, we can interpret that lambda 2 is a larger magnitude. So in this case, it's a larger negative value. So it's a more negative value. And so that for that reason, that exponential dies away quicker than V1 does, the V1 mode does. So if they're both unstable, you get a very similar picture. The only difference is if you start here, that you move outwards. And so in that case, again, you're moving outwards along V1, and that's happening relatively slowly. And here you're moving outwards on V2, and you're moving relatively quickly. So these represent slides that go into more detail than I'm going to expect you to work through on a quiz. But it's worth noting just so anyone that's interested can kind of go into a little bit more detail. So right now, in the past example, I said that lambda 1 is not equal to lambda 2. So in the particular case where lambda 1 and lambda 2 are the same, so you have repeated eigenvalues, you can get some particularly peculiar behavior. And so they are still considered a node because they're real valued and they're repeated. And so if they're positive, then you get this unstable behavior. And if they're negative, you get this stable behavior. If you get stable, then stable, you get either of these behaviors. And if you're unstable, then you get either of these behaviors. So what makes the difference between this upper part and these lower figures is has to do with algebraic versus geometric multiplicity. And so these could be some terms that kind of ring a bell in your head. And so I'll just go through this really quickly. Again, this is something that you don't really need to understand that I'm going to test you on, but it does really help build some intuition on the whole system and how eigenvectors and eigenvalues play a part in the trajectory of the system. So this is just a reminder that our solution looks something like this. And so these are characterized by eigenvalues and then the corresponding eigenvectors. So if you have a repeated eigenvalue, you don't necessarily get independent eigenvectors. So if all your eigenvalues are distinct, then that means that all your eigenvectors that correspond to those eigenvalues are linearly independent. So you already have n of these that are linearly independent. When you have a repeated eigenvalue, you can either continue to have n linearly independent eigenvectors, or you can effectively lose one. And so the count of repeats is called the algebraic multiplicity. So that's the number of repeats of eigenvalues. And the number of linearly independent eigenvectors, that's called the geometric multiplicity. And so when those two are the same, as it is guaranteed to be up here, then you have all the solutions that we saw before. And that's where you have essentially this star kind of behavior, because essentially you get the same behavior in all directions. There's no, because lambda 1 and lambda 2 are the same, there's no curving like what we saw. One mode doesn't go faster than the other. Those bottom figures that we saw in the past slide happen when you have deficient geometric multiplicity. And that's because when you have this case, you don't have a linearly independent V2 to go in here. And instead, that factor that multiplies this is called this generalized eigenvector, and it's really related to, and there's a portion of this that's linear and relates to time. And so you would have seen something like this if you look back at your differential equations course. You would have seen something pop up like this in some of your solutions. Again, this kind of goes beyond the scope of what we need to talk about in this course, but that accounts for the kind of wonky trajectories that we saw in the previous figure. So the last major category, now that we've seen all the different kinds of real eigenvalue solutions, now we look at when you have complex eigenvalues. So lambda 1 and lambda 2 are complex conjugates. We know that complex values occur in complex conjugates, so you have to get, and we only have two solutions, two values for eigenvalues here. So you're going to get some real value plus or minus I times some imaginary value. And so since our solutions look like this, where lambda 1 and v1 could be in general complex. Now, so when we expand this, this single term becomes a real part times an imaginary, a piece that's oscillating that includes an imaginary piece. And then this eigenvector, v1, can be separated into its real part and its imaginary part. And so this corresponds to effectively this particular eigenvector, and then you can, this eigenvector mode, and you could do the same for the other eigenvector mode. And what you'll find out is in the end, x is a real value. So what ends up happening is these imaginary terms that appear here cancel out between the two modes, essentially using a plus ib and a minus ib into two different modes that look like this. Those end up canceling out. And that's actually a nice activity if you wanted to take an example that has complex eigenvalues and show that in the end, if you simplify it, your x of t values end up being real, despite the fact that that you have these imaginary pieces in each mode. So here in the phased portraits, I'm showing the kind of nice figures from this this website. The really important bit here that I want you to remember is that it's this piece right here that determines the stability. So this oscillation accounts for the spiraling nature, essentially the circulating nature. The fact that this spirals, in this case, these are stable. So in that case, they're spiraling in, the radius is getting smaller. So those are stable. In here, they're spiraling out, and so the radius is getting bigger. And so that radius is really determined based on the real part here. And so that's why, that's one of the ways in which you can think about the stability being a function of the real value of the eigenvalues of the matrix A. So the distinction between the counterclockwise and clockwise spin, technically it's determined by this particular coefficient in the A matrix, but that's not really a super important piece for you to remember. You should always be able to figure out the orientation just by testing the direction, the derivative at a particular point. So finally, a specific version of the last one where we had complex values is when the real value part is 0. And this is really a case where we have this idea of marginal stability pop out. So here you would have had e to the alpha t, but since alpha is 0, this term just goes to 1. And so you're just left with essentially the circling portion of this. And so that's why you either get clockwise or counterclockwise spinning motions. And so depending on where your initial condition starts, you would move around based on that. So this describes all of the different types of behaviors that we can see out of these 2x2 state space systems. An interesting way of presenting all of this information is to do this on this plot that plots the trace of A versus the determinant of A. And we know that this discriminant here, essentially when this discriminant is negative, we enter inside this parabola, and that is this region, and that's when you get complex eigenvalues. When this discriminant is positive, you're outside and you get real valued eigenvalues. And so these provide a nice way of characterizing all the different kinds of solutions we would expect to see out of 2x2 systems. But the important thing is that these notions of modes and understanding how the different modes play into the overall stability of the system really generalizes nicely as we go to higher order systems. So now that we've seen a couple different visuals on how to characterize the stability of state space systems, we can kind of come back to transfer functions and do a similar approach. So here we're going to have a homogeneous, so equals 0, nth order differential equation. In general, we could have some sort of transfer function that looks like this. And again, one of the what we saw earlier in an activity is the fact that the zeros of the denominator polynomial, we called those poles, those determine the stability of the overall trajectory of the system, y of t. And the reason for that is because when we do our partial fraction expansion, we essentially get terms that look like this, and these pj, essentially the different poles that are the roots of this denominator polynomial, end up being, when we take the inverse Laplace transform to get these exponentials, they become the exponents of this exponential. So each term in here is a mode, and that mode is going to be either stable or unstable depending on the sign of the real part of that pole location. So again, poles, because they're the roots of this polynomial, they can be complex. But then the real value is what determines the stability. And so then what you're going to see in your homework and at other activities is that these coefficients really depend, in the homogeneous case, simply on a combination of the poles as well as the values that you have that construct the numerator. And so we're going to start calling those zeros. We'll get into that eventually. But for now, those, because this is just a homogeneous differential equation, those will just depend on the initial conditions that you have of your system. So similar to the plot that we saw before, the diagram we saw before, we can kind of think about the complex plane. So this is the real value of S and imaginary value of S. And depending on where your poles are, that tells you the stability of your system. And so if you have a pole that is positive like this, and in this case there's no complex value, it's only real because it's on the real axis, then you just get this exponential growth, similar to what we saw in the first order example. Here, if you have a pole that's 0, that mode looks like just constant behavior. Again, very similar to the first order. If you've got a negative pole, then you get stable behavior in that mode, and that's again just like our first order example. But now that you can have 2 poles or 2 roots of this denominator polynomial, now you can get other more complicated behavior that come out of complex solutions. So for example, here you can have it's negative in its real value. The pole has negative real part, but it also has an imaginary part. And so that pole would yield this oscillatory behavior that you see here, but it's stable because it's slowly decaying away. A similar pole that has the same imaginary value, but has positive real part, the amplitude will be increasing, and so that's an unstable. And so it's really this dividing line here where the real value is negative if you're over in the what we call the left half plane, and that's what LHP means. And if your pole ends up being in your right half plane, those are inherently unstable. And right here in the middle are these marginally stable cases where you have either a constant behavior or pure oscillation. And so if we were talking about the state space approach, we could connect each one of these to a different phase plane model. For example, this would be a phase plane model that would represent simply a center that is oscillatory, but no decaying or increasing radius for that focus. So it might be a good idea for you, and this is one of the things you'll do in Lab 1, is to, or at least motivated by Lab 1, is to understand how each of these plots in trajectories match back to the phase portraits that we saw in the state space version. And so again, just to emphasize, we've talked about this system being asymptotically stable, and that's going to be a function of the poles of the transfer function having negative real part. So that's what we've already established, and that's really determined based on the left half plane and right half plane location of those poles. And again, we talk about the overall system as being stable or unstable, and we talk about each individual mode as being unstable or stable. And finally, essentially all poles, what we're emphasizing here is that all poles of the transfer function need to have negative real part if you want your system to be stable. So all modes have to be stable. Marginal stability happens when you're on this real axis. And essentially what I want you to appreciate right now is that those are kind of tricky cases, and depending on how many of those you have, you end up either being stable or unstable. So it's kind of depending on context. Marginal stability, essentially having a marginal stability mode can either end up being overall unstable or overall stable. And then if you have any poles that have positive real part, that's automatically going to make your system unstable.